Okay, welcome to Lecture 6 of Introduction to Geographic Information Systems. I can't believe we're already at Lecture 6. I may have to slow down a little bit so we can make sure that we're all caught up on our labs and everybody knows what we're talking about. But today we're going to be talking about GPS, which is a different form of data gathering than the normal census that we talked about last time. But it's a very important aspect of using um, GIS in a lot of ways. I mean, GPS and GIS, in so to speak, kind of go hand in hand, or most people think of it in that sense. So, what is GPS? I mean, a lot of times we have it in our mind that, oh, we have GPS on our phone, or it's in our car, or you even have the little key tags that are essentially they're sold as though they're GPS located. What is GPS? They're usually in our mind that we just kind of think of it as a way of identifying a location on a surface, right? I mean, having a reference system and a measurement of a location that's accurate to a degree, and that's normally all we think of it as such, because there's a lot of things that are happening behind the scenes of a GPS that we don't always consider. So at its base level, right, it's a method for surveying, and it uses satellites that are orbiting the Earth at high altitudes to get the location of that point on the Earth's surface. It allows for very accurate geodetic surveys, which basically means that you can have an accurate measurement of where you are. It's not just kind of a rough guesstimate like that you would have on a normal survey. It allows for like very high resolution imagery. And measurement, for that matter. It's more measurement in this section, but it also allows us to have accurate imagery as well. And it's done by using specially designed receivers, and so that's what's actually in your car, in your cell phone, in your keychain, all of it. There's a GPS receiver that's, when positioned at a point on the Earth, it measures, or it receives the measurement of, or it creates the measurement, I should say. It creates the measurement of the distance from that point, or you, to 3 or more orbiting satellites above the Earth. And so you basically are always, these satellites are always projecting their location, and it is then measured by your receiver of the distance, and you're basically able to take a calculation of 3 or more of those satellites that are consistently beaming their location into your receiver to triangulate. That's where where we use that word, right? Triangulate the location of a point on the globe. And through geometric calculations, that point is kind of determined, right? That's where we're at. This is a great example. This is XYZ, basically your plane, your ship, and your van, and the time from 4 satellites to calculate position. So what I'm basically trying to show with this example is that there's GPS receivers everywhere. There's GPS receivers in your car, in your phone, on a ship, in a plane in particular, and there are 4 satellites that are essentially calculating beaming their own position into the receiver that is housed in each of these navigatable vehicles. And there is a calculation that is happening behind the scenes that's essentially accounting for the location of all of them and giving you an exact point of where something would be. I will kind of explain a little bit later why 4 satellites is actually the optimum and 3 is only like the bare minimum. So let's kind of back off a little bit and give a little bit of a history lesson. I want to make sure that we kind of know what we're dealing with, because GPS, everybody thinks of GPS as like this super accurate method and that there can never be any mistakes. And well, that's just quite frankly not true. So let's talk about one of the most important, and I believe the original here, Navstar GPS, Navigation, Satellite Timing and Ranging Global Positioning System, right? It's developed by the US DoD, and it has 28 to 30 satellites orbiting the Earth at high altitude twice a day. So each satellite orbits the Earth twice a day, and it transmits precise time and position information for worldwide and all weather navigations. However, while that is what it does now, it was not until the early 90s, actually maybe even the mid 90s, and I think it was Clinton that did this, in which he more or less turned off inherent error in the GPS system. Prior to, I believe it was Clinton, turning off this inherent error, which is essentially a switch in which the military injected random error points in their GPS system so that it would be very difficult for the enemy to use the positioning system against them. They injected this random error, and that had to be accounted for when you were using it for civilian purposes, and it wasn't always as easy to do. And technically, if something were to happen, the U.S. government and DoD can turn this inherent error back on with the flick of a switch. Which is kind of a terrifying, horrible thing to think about, in the sense that you have freedom until we deem it no longer to be acceptable, and then you don't actually know where you are, and we can basically transmit complete wrong measurements into your own navigation system without really having to tell anybody for any reason why. But I digress. Moving on. So now Navstar has kind of changed up a little bit, and so now there's only 24 satellites across 6 orbital planes. So what that more or less means is that you have 6 distinct paths that are covering the spectrum of the globe and on different planes, and that these satellites essentially split each of these planes into 4 equal units. So essentially 90-degree span in a circle, right? There is no other satellite on this plane except for the Navstar, and so they split it in half, and they orbit approximately 20,000 kilometers above the surface with a 55-degree inclination, and satellites complete an orbit every 12 hours. So essentially those 4 satellites within an orbitable plane are going around twice each day. This is essentially what it looks like. This is for Orbis, and it shows the 27 satellite coverage in 1998. This is kind of a cool photo. I'm sure I could have found a much newer one, but I really enjoyed how this really outlined all of the tracks and trajectories of every single satellite within the network, and it really shows the coverage. And so you can kind of see that while it does cover the majority of the habitable area, there are areas that it does not actually cover, and that I think that you'd find that there is some GPS issues the closer to the Antarctic or to the poles. Let's just leave it there. The closer you get to the poles, the more error there could be within these GPS unit measurements. So let's kind of move into the operation aspect and see if I can hopefully make this a little bit clearer and I don't confuse you anymore. But basically, the basis for the operation of a GPS is triangulation. I said it before. It requires a satellite, it requires a GPS receiver, and you need at least 3 to determine the location of that GPS receiver. When I say determination of location, you need both the location of the satellite with a coordinate system that can be interpreted by the receiver. And obviously you need a coordinate system, so it's an output. So there's a coordinate system to both convert the location of the satellite and the GPS receiver, but also it needs to be a coordinate system that's understandable to the human eye, so you kind of have some understanding of where you are. Satellites, like I said before, more or less continuously broadcast their time and location at all times, and so you essentially get down to, I think it's 1/10 of a second. It could be just a single second, but I believe it's into 1/10 of a second of its location and the time, and it basically is a way of calculating the distance from the GPS receiver and the satellite, which receives the signal, calculates the distance between the satellite, and you essentially use that distance to get a location spectrum of where you will likely are. And then the more satellites you add, the finer and finer that location gets. And I believe we'll get into that in a couple of slides. Yeah, in a couple of slides. And so it will be a little bit more clear with a graph. And then the time span is the time the signal takes to travel from the satellite to the receiver. So, basically a simple physics equation. This determination of the location. So like I said, for the location of a GPS receiver, there has to be 3 or more simultaneous measurements to determine the location of the receiver. The more you have, the better, until a spectrum of, I believe, 10. I believe once you hit 10 satellites consistently transmitting their location into your receiver, you are no longer gaining a reduction in an error or location, you're simply just kind of being redundant at that point. And a coordinate systems is obviously a GPS is going to provide its position to the user in either geographical, UTM, or state plane coordinates, along with the altitude, depending on where you are in the world and what you're looking for. So are you looking for metric? Are you looking for the foot and the state plane measurement? What it really kind of depends. Okay, now let's kind of move on to this aspect of why you need more than just one or two satellites. One measurement from a satellite is going to narrow your position to the surface of the sphere. So if you are, 20,000 kilometers above, if when you get that point, that first satellite, the only thing it does is give you it essentially is a way of acknowledging that you aren't just floating off in space, that you're on a sphere, right? That this is essentially, it knows that you're somewhere within this orbit. Two satellites narrows your position down to the intersection of two spheres. So essentially basically saying like, yes, they're somewhere within this circle that is the intersection of the two spheres, but it's still not going to be a very small circle. It's still not an accurate enough measurement. It could basically say with two satellites, you're probably somewhere on the eastern seaboard of the United States, or you're in, Mongolia. But we don't exactly know where. Somewhere in that range. And that really doesn't really help you in that sense. So three measurements narrows your position to just 2 points, because the intersection of a circle and a sphere is 2 points. It's basically saying like when you add that third section, you have narrowed that original circle down to just 2 points on that circle. However, while this is good enough, because more often than not, you can have an inherent programming rule built into the GPS that says you take the point that makes sense. More often than not, when you have this set of 2 points, 1 point is a logical location, i.e. the location you're actually at, or wherever the GPS is, and the second location is one that makes absolutely no sense. Either it's somewhere that is in the middle of the Indian Ocean, or it is someplace that is completely not even on the globe. If you see something on the globe, there may be a little bit inherent error that's happening with that first point, because technically everything should always be acknowledged to be on that surface. But what I'm getting at here with this example is the idea that only one of these 2 points makes sense for your location to be. When that fourth measurement comes in, you narrow the location of that position down to a single point. So that fourth satellite is where it becomes key that you've essentially eliminated that incoherent second point that just makes absolutely no sense. And this is kind of, I don't have any other graphs from this, and so I kind of want to make sure that we're talking and we acknowledge that when I said previously that I think it's 10 that you can go up to and get at a reduction in error and location clarity, it doesn't mean that 5 is going to all of a sudden split up and create 2 points again. It's more of a way that's saying 4 satellites is going to get your location down to something on the Earth as close as something, let's say, like 30 meters in a location. Like you know essentially that you're close enough to get somewhere that is on a highway, and you know that if you miss your exit, the satellite's going to know you missed the exit within like 30 meters. When you add more satellites beyond 4, all you're doing is essentially narrowing down that level of clarity. So from 30, it could be 10. From 10 to 5, 5 to 2.5, 2.5 to 1, 1 to half a meter, to however long you go until 10. And that's kind of when you start getting into redundancy and you're no longer able to reduce this inherent error down. So, again, we're kind of talking about this in just another way. So you have a single sphere that's acknowledging, or a single satellite on a sphere acknowledging you exist on the sphere. 2 measurements more or less shows that it's a circle, and 3 gets you to those 2 points. And this is just a different way of showing it in more of a 3D-esque way. Okay, so we've talked about how triangulation works, how GPS satellites essentially work. Now let's talk about the other side of this, about the GPS receiver. Most people, for at least in the United States, are going to assume when they hear the word GPS, they're going to see their phone, and in a sense, their phone is the receiver, right? Now, this is true in the sense that, yes, phones have GPS receivers, but there is more to it, right? GPS receivers can be handheld, or they can be installed in something like aircraft, ships, tanks, submarines, cars, trucks. Um, I don't think they can be installed in humans, because technically you're going to need some sort of way to power that receiver. But there is a lot of things that happens with the transhumanism movement, and so I'm not going to cut it out and say that yes, you can install this in a human being, because it would not surprise me all that much if there was in fact someone experimenting with a GPS receiver in the human body. Anyway, I digress. That's, kind of its own unique thing. This photo here is a park ranger that essentially has an old school GPS unit that is pretty accurate. This is going to give the location of a person probably within a half a meter, according to the little bobble, the staff on the back. Yeah, it's more or less of a survey GPS. So GPS receiver uses radio channels in the sense that it receives the location through radio channels from the satellite. It has an internal clock in which it is a way of measuring the time received from the satellite. So in other words, you have the time it is for the internal clock of the GPS receiver, as well as the timestamp of the satellite when it sent out that location received by the GPS unit. And the computer that is built in is a way of basically performing this calculation of getting the distance of the GPS unit from multiple satellites. I basically have already said this, but radio channels, it needs one or more channels to receive the signals from the time the signal is sent, and a pseudo-random code to identify the signal. I did forget about this section, and where basically you need to know what satellite is what. So each satellite has a not really random code, but it's numbered to us being the user. It doesn't mean anything. It's simply just an identifier that is created to give the unique identification of the satellite. And then obviously the internal clock again is synchronized with the satellite in order to calculate the signal travel time precisely. So you don't really want to have any error in that location or in both the time sent or the time received, because any single type of error within that synchronized clock is going to basically skew the distance and the location of the receiver. So the computer, again, calculates the distance and location, and it also stores the locations and readings. So that's when you think of a total station, right? You take the specific points of a total station, using a total station, I should say, but you're not writing those points down most of the time. I mean, you can. There are some old school total stations that don't have a large enough internal computer in which you essentially are handwriting the locations of points before you put them into a GIS, but most total stations, at least modern ones, are able to store those internal points and convert them into a usable data set for a GIS as well. And it also calculates the satellite availability. So essentially what this means is that there's more or less a schedule to explain what satellites are more than likely going to be able to be received from the point that the location of that total station or of that GPS receiver. So there are different types of GPS. Really what it comes down to is there's the autonomous GPS with one receiver unit. That is your standard everyday GPS unit. It's your phone, it's your car, unless you have a very special car, in which case, you probably know a little bit more about this than I do. But if you're a consumer of GPS technology and you are not trying to do some serious analytical measurements of spatial, of really anything, so, landscape archaeology or agriculture or something like that, and where you require very precise measurements of something within a location, more than likely you're using an autonomous GPS. Differential GPS is slightly different, and it basically is a way of more or less avoiding the selective availability of interference. So that is the interference that I mentioned about with Bill Clinton, kind of turning it on and off depending on if there was a threat to the United States. And differential GPS allowed you to more or less verify the location, because that way you wouldn't have any wonky measurements. So it would seem at first that autonomous GPS is essentially everything that differential GPS is, because we no longer have this error that's built in, and therefore autonomous GPS should be just as accurate as differential. In a sense, that should be accurate. In most cases, I would argue that you can probably get away with autonomous GPS units as long as they're very good and they have a level of error that's built in to be acceptable for whatever you're doing. So you can get autonomous GPS units, like a single receiver unit, down to, I want to say, under a meter. Yeah, in location on the globe. But that may not be enough, or something else may be needed, or you may need to guarantee that you're not working in the U.S. I mean, maybe you're working on a different countries and they still have different selective availability interference, because that is the case, that there are some satellites that do project interference. And so differential GPS is a way of basically covering bases and guaranteeing that there are no mistakes in the readings of the location. So it more or less includes what you call wide area augmentation system, and that's the system that's built in to combat this selective interference. So the U.S. government, oh, I have it wrong, 2000, but that is still Bill Clinton. The U.S. government used to insert random errors in the signals in order to maintain optimum military effectiveness of the system. So just like I said, there was a concern about the enemy using our GPS systems. There was probably never really a name to the enemy. I would imagine prior to the early 90s, that would have been the Soviet Union, but prior to the collapse of the Soviet Union, I would find it hard-pressed for them to actually name someone using our GPS systems. But like I said, it was turned off in 2000, and we've been pretty much free ever since. There was some talk of reinstating it in, I believe, 2010, but it was shot down. Differential GPS is essentially, a way of designed to compensate for those inserted errors, and it was and still is used after 2000, really just because it allows for a better location reading. You just can't get the level of accuracy and level of the minimal error readings that you can with differential GPS, like you will get with autonomous. So differential GPS, what does this really mean? It uses two units, one receiver that is placed at a known X, Y, and Z. So you need all of the locations, more or less basically being a guaranteed location where you know where this is on the globe. And then you take that location of those coordinates and then as the control point, more or less, to detect any inserted areas and calculate the needed corrections. And then the needed correction information is used by another receiver to overcome its selective availability interference. It's also a way of basically guaranteeing the measurement of how close you are. So you have 4 satellites that's giving you the point from space. But this secondary control unit is also a way of measuring the distance between the two, which also gives you a way of measuring the surface, the distance across the surface rather than just on space. And that little bit of change allows for just slightly better reading with differential GPS that you can't get with autonomous GPS. So just a couple more things on the differential GPS. The corrections can be made both real time in the sense that the radio modems that more or less continuously project the distance or the location of that control point can allow for a correction that's done while collecting points, and it's basically a program that just needs to be run at the same time as data collection, or it can later be considered when you're entering these points or filling these points or clarifying what you're seeing as data onto a computer in a program like a GIS. There are a series of radio beacons to transmit the DGPS corrections for accurate navigation. What that basically means is that we're kind of talking about those that WAAS network of where there is a consistent network that's built in to account for this error rate, that you may not just need to have your own single receiver, that there are ways of verifying the exact location. This is what I mean by that. So you have the satellites that are all giving you the location, and then there's also a satellite-based correction, which is your roving receiver, and then that little beacon off in the corner is the reference receiver. So essentially, those GPS satellites are both sending their location to the GPS beacon, which is a known location, and that differential correction is being sent from the beacon to the roving receiver. I like this little comic. I think it's a pretty good description. Okay, let's talk about like the WAAS system, or the differential correction service that I mentioned previously. So WAAS is a real-time differential correction service operated by the FAA. It provides flight and approach navigation for civil aviation. So more or less, the WAAS is really originally designed to take care of pilots. Previously, the only people that would really need or want something to secure their location when there was inherent error built in is pilots. I mean, you don't want to run that risk of being up in the air and not knowing where you are. The coverage of WAAS is the continental United States and kind of parts of Canada and Mexico. It covers 25 ground reference stations throughout the United States. These reference stations kind of compute and transmit data to the WAAS satellites and then retransmits them for WAAS-enabled GPS receivers. So the information sent to sent down from normal satellites to WAAS stations, they then beam that back up to another private set of satellites, which essentially gives the location of the accurate data. More or less a buy around of the inherent data in the system. Most recreational grade GPS receivers now include WAAS receivers, so most of the time, if you were to buy into this system, you could receive this corrected information without having to worry. But like I said previously, the inherent error has been turned off since 2000, and it has not been turned on since. So you're kind of buying into something that is more of a security, just in case, rather than something that you're going to use every day. So we talked about this. Signals from WAAS satellite or from GPS satellites are received by the whole reference stations on the ground throughout the network, and each of these precisely surveyed reference stations kind of determine the signals and then see if any error exists. If they do exist, they beam that corrected data back up to specific satellites that are part of their network and send it out to other receivers so that they can all be corrected. They're linked to join this total network, which is in sense for aviation. So what's the point, right? I mean, I just said it. Why does it matter? Interesting enough, it improves the accuracy, integrity, and the availability of just basic GPS signals. I mean, and it really provides the groundwork for navigation systems for aviation. It is owned and operated by the Federal Aviation Administration, or the FAA, and it's real time. It is free now, which I did forget. I actually had to add this in later as I went through some more research. But prior to 2000, this was not free. It was a way of kind of discouraging regular people from buying into this this differential GPS system, reducing the number of people that required it, and basically securing that there was always going to be available for pilots. Since this has all been turned off by, or the inherent data or bias has been turned off. Inherent bias. It's more or less the same thing. The inherent error rate has been turned off since 2000. The cost has become free because this is now a service that is kind of doing the same exact thing as a normal satellite. Here you can see the locations of all of these WAAS stations. As you can see, they do cover large areas. They are all in U.S. territories in the sense, but because of their wide area augmentation system, which is essentially a basic fancy way of saying that it covers a large area, you can see how it does, and it will reach into areas that are not part of the United States. So the FAA does not have a monopoly on differential GPS services. There's obviously one that you all may have heard of, OmniStar, which I believe is in GM vehicles. It's again, a real-time thing. GM bills this very much as an emergency service. You get in an accident or you need something, you click the location and you say, hey, I need to know where this is. And that, in a sense, is an emergency system, but it's an emergency system that is part of GM. So OmniStar, in terms of the satellite differential GPS network, is it's really the same idea as the WAAS system, but it's a little bit larger coverage, right? So again, it's a network of reference stations, but in this case, it's 70 reference stations with 3 network control centers. So kind of I believe it's a continental wide area, and there are some movement into, but it's a worldwide coverage. This is not something that's just in the United States. It's entirely, it's everywhere on the globe. But it does cost. It is not free. I don't have the exact cost, but it is not free anymore. So let's kind of move into like your types of GPS units. So you have your static, where there's 2 or more receivers to receive data for a long period of time at a fixed location. So a way of kind of guaranteeing the location. And chromatic is 1 receiver placed at a known location while the other receiver moves around from one point to a point. So more or less, this is kind of explaining the differential GPS into 2 different spaces. And so you have the real-time chromatic, or the RTK, which is the real-time transmission of one's receiver moving from point to point. This is your total station. So what are the advantages here? So it's fast, it's more accurate, lower cost than manual approaches. Disadvantages of using GPS for getting the actual place is it's it can be obstructed. There isn't always a clear line from a bunch of satellites, and that makes it kind of difficult to use in certain locations. As we continue to increase these networks, we're kind of getting into more locations, and there's really minimal obstructed areas, but depending on the time of day or the satellite system network you're within using the GPS for, it can change, but it's something to consider. Okay, we're going to finish up today kind of by going over how this differential GPS of OmniStar works. We're just going to kind of go over everything again. As you can see from my cute little animation, you should already have a pretty good idea of how this all works, but I'm just going to summarize it. We're going to talk a little bit about what OmniStar says about this graph, and then we're going to finish up, and that'll be it for today. So obviously you have these 4 GPS that are beaming their location down with a timestamp of the location. That is then picked up by both the static receivers that are part of the OmniStar network that you can see on the ground as those square blocks, and they're picked up by the guy with the 4-wheeler and the GPS unit mounted on the back. While the guy is driving around on that location, he does not know inherent bias has been built into the system, or he doesn't care, or it doesn't really matter. That bias or error is picked up by the static locations and then transmitted through a virtual network to a projection station that essentially projects the error, the corrected error, back up to a separate series of satellites that then beam the location down that has been fixed for the user. And so the actual user's location of this GPS receiver on the 4-wheeler has now been error corrected. What OmniStar basically says is that their unique virtual base station technology generates corrections optimized for the user's location. OmniStar receivers at a monitor site output both high-quality RTCM SC104 version 2 corrections, which is a fancy way of saying that they fix specifically related to differential Latin long, as well as state plane and a number of other things. And then multiple OmniStar GPS monitor sites send GPS corrections via lease line to the Houston control network, where the data corrections are checked and repackaged to uplinked to their L-band geostationary satellites. Correction data is then received by user equipment and applied in real time. That's taken directly from their really from their little differential GPS website, and where they say what everything does. There's a lot of fancy jargon in that. What it basically says is that not only do they correct and project differential error, correct and project error built into a GPS system, they also do this per use on a user basis. So the location of the user is, or the GPS receiver that is fixed to the user, is going to be only receiving information that is about that location. It's not going to be a broad spectrum cast of like it would be in the WAS. It is specifically repackaged for that user and their location. Okay, So let's finish up. Today has been kind of a quick summary about GPS. There's a lot of mathematics that go into GPS. You have to have the distance of and the triangulation of the locations on their fixed point, and so there's a continuous equation and processing done by the GPS unit there. But there's also the fact that you kind of have to understand how satellites work and how networks work. I've tried to do my best here to really just kind of keep it on a general aspect because I mean this is an introduction class, and personally I do not feel that you have to be proficient in all things GPS to be an analyst. Most of our job here as analysts of geospatial data is more to understand how the data is created and how it has some limitations. Anything beyond that is more up to an engineer that is working to build the system. We simply are users of the system for another purpose, and that's something that we need to always consider. In to give the arc today in a kind of an archaeological spin, I don't expect archaeologists, and I think it's kind of an unrealistic expectation to expect archaeologists to perfectly understand all the ins and outs of both a GPS system and the satellites that produce that network. However, that doesn't give individuals the right, I guess, to kind of simply ignore that and just take it for granted. It is important that we have some understanding of what is going on so that we understand what processes create the data that we're able to use and so happily use. I think if you were to look at archaeological news, save for small or just articles in general written about specific finds or locations, you'll find that many of the major things that receive news attention or mass media attention are really things that are related to spatial. I just read an article from the BBC yesterday, so June 2020, discussing how all of the satellite data for Britain from 2018 has been processed. During that year, there was some pretty severe droughts across the entire island, and that actually allowed for the creation of imagery, satellite imagery, that shows a large number of villas and military forts that were built by the Romans without having to do any sort of excavation. Now this information would not have been possible, and we would not have had this spatial coverage available both with satellites and the fact that the drought conditions were so perfect. But this is something to consider, right? That spatial technology and how we use and integrate spatial technology into our everyday lives is something that we often take for granted. But as analysts and as practitioners of GIS, this is something that we need to be aware of because it is our job to be able to take this whole holistic approach to modeling the real. And I think I'll leave it there. I hope you all have a great week or day, depending on where you are, and you'll hear from me soon. Goodbye.